Okay, dear students, so let us see what is in this video. We are now going to find the time period for the spring mass system. And while I do that, like I would be completely showing you the derivation, you have to concentrate on how I am doing that. Why? Because the pattern, the procedure that I'm following, the same procedure will be followed everywhere for every kind of simple harmonic motion. And in paper too, you would be getting these kind of questions only. Like if there is a simple harmonic motion going on and the expression for the force is given, the paper two question will be asking you to find the time period. What will be the frequency? What will be the time period? These are the pattern. This is the pattern that you have to do. These are the steps that you have to follow. Let us concentrate on this, and the topic for today for in this video is to find the time period for spring mass system, which will serve as a very good example for us. Spring mass system. Okay, so spring mass system is in front of you on your screen. So this is the mass which is moving, and we can just write m here. The spring constant value is given to you, that is k, and we want to find like what is the time period for the oscillation. Okay, now, so when it is displaced with x, this is how you do it. Okay, like this is the step number one. Step number one is the find the expression for restoring force. Find the expression for restoring force. Now, if let us say at any time t, the displacement randomly, it is given as x. So the spring is now applying a restoring force on the body in the opposite direction because it wants to restore the body to the mean position or the equilibrium position back again. So there is a restoring force, and without restoring force, there is no simple harmonic motion possible. So this is the sine qua non condition. Restoring force has to be there. There has to be an expression mathematical for it, isn't it? Let's see. So we will invoke the Hooke's law here, and we will say, according to the Hooke's law, F is equal to negative kx. Clearly, the force is directly proportional to negative of the displacement. Accordingly, you can find the acceleration, and this is the fundamental condition for simple harmonic motion, which is fulfilled here. Absolutely correct. So this diagram in front of you, spring mass system, is absolutely a simple harmonic motion, and we can talk in that term. So having said that, step two is we want to find the acceleration. So F can be written as m into a, inertial force. It is minus kx. Accordingly, we can find the expression for a, which is this. This is what you have to do every time, okay? Find the expression in the terms of, find the acceleration in the terms of x. After that, step three. In step three, what are we going to do? We will say that we are going to compare this equation with the fundamental equation of simple harmonic. And what is that? A is equal to negative omega square x, which clearly means that omega square, this is step number 4, which clearly means that omega square is equal to k by m. So omega square is equal to k by m. This is the expression that we were looking forward to. Omega will be replaced by 2 pi by capital T. We will substitute in it in this, and then we are going to find the expression for the time period, that is T. Okay, so what now? I think I must move myself. Okay, so let's go for step 5. On comparing omega square is equal to k by m, omega square is equal to k by m. Omega is written as 2 pi by t. K by m is taken square root here, and so the time period is indeed coming out to be 2 pi root of m by k. This is the expression that we were looking forward to. So there are two things that you have to note. Point number one, what are you doing in this? What is the expression? This expression is given in the data booklet, so need not to remember it. You can just relate it. That is one thing. And the another is that what is the method? What is the expression that we have followed to find the expression? And how is this procedure to be applied on other scenarios that will be given to you in the examination. So I will share some videos after it also, in which we could have done that, if I have those videos then. So t is equal to 2 by root of m by k. Now what happens in paper 2 is, some expression is given to you. Like for example, they will say that there is a body which is floating inside water, like this, and the expression of the restoring force will be given to you. They will say that the restoring force is given by something, something will be given like mg divided by the coefficient of viscosity into x, something weird thing I'm talking about. I'm not even sure about what is given and what not be. Something of this kind will be given. Very easily, we will just replace Hooke's law with this. Then we will find the acceleration in the terms of x. We will compare omega square with the another expression suitable for this, and we will find the expression for the time period. This derivation that is on your screen is very important. Watch this video twice or thrice, and do not forget to, like, do this thing by yourself couple of times. It is very important. Thanks for watching. See you in the next video. All the best.